Good afternoon, everyone. The main idea for my research is understanding the origin of a special phenomenon in our universe called a black hole. So for this presentation, I'll be going through my research project, which is predicting the origin of black hole seeds using cosmological simulation. By the way, I'm Joshua Olatunji, and I'm mentored by Dr. Gillian Bellavori. Our big question is how do massive black holes form? Studies have shown that massive black holes are centered at the center of their host galaxy, and this is giving insight to them being a major role in the evolution of of galaxies. There are two types of black holes. We have stellar black holes and massive black holes, and for my project, I'm focused on massive black holes because their formation is still a question that's yet to be answered. And how do we tackle this? We tackle this by showing three theoretical pathways that could lead to the formation of a massive black hole seed. This starts by a gas disk which is surrounded by dark matter. And the first scenario illustrates a stable gas disk which cools to form stars that are like up to 100 times larger than the sun. And if the stars formed at 300 solar masses, there's a possibility of them collapsing to yield black holes that are 200 times larger than the mass of the sun. The second scenario involves a globally unstable gas. So we have this material and the gas disk rapidly falling to the center, and this merging of particles creates a very large star, which collapses into a black hole. And this forms a black hole, which is about 1 million times the mass of the sun. The third scenario involves a local unstable gas flowing into the center. Locally unstable means just a little portion of, of the gas disk. So these gas fragments form into a dense cluster of stars. And this cluster of stars merge into each other, which collapse to yield a black hole, which is about 1,000 times more massive than the sun. So how do we tackle this problem? Here's a video of the simulation we use, which is the M-body and smooth particle hydrodynamic simulation. This simulation is a system of dynamics of particles under the influence of a physical force such as gravity. And we make use of Python and a package in Python called PinBody to analyze snapshots of this simulation, which have data embedded in them to get results of our project. So what are the results we've gotten so far? First, we have to understand or know if any black hole is forming in the simulation. And here's a simple histogram plot that shows the frequency or the numbers of black holes formed versus their time formation. And this is just a snapshot of the simulation, and it's approximately 11, redshift 11, which is like a couple years after the Big Bang, which makes sense because at that time, there will be a lot of activities and mergers, so which is a reasonable way of forming black holes. So we validated our major theory because I mentioned earlier on that we have stars or particles colliding with each other. So we validated our major theory, and this is a 3D plot which shows two galaxies having a plot that shows the trajectory of two galaxies. The first one has a larger black hole compared to the second one. As you can see, they are coming from different points in space, and at some point they merge together to form one black hole. So this validates major theory of the formation of massive black hole. That means black holes merging together to form this larger black hole. And this was validated also from the increase in mass gotten from our data. So our future work includes creating a more visual representation of mergers for better understanding. and also comparing to other snapshots in the simulation to see if our three predicted pathways to the formation of massive black hole holds true. Here's my reference, and we also want to thank the CRSP program and our NSF grant for making this work possible. Thank you so much.